I know this is the very last presentation at this year of Black Hat, and most of people may go to party already. If you get show up here, you must be a very big fan of either IoT or Honeypot, or you just hate parties. So in the next 15 minutes, we will share our experience on how to build a honeypot for the IoT devices. This is the joint work with my colleague Xing, Yanhui, and Xin. So at the very beginning of the presentation, just a little bit of background about ourselves. My name is Tongbo, and this is my third time present here in Black Hat. And currently, I'm the principal security researcher at Palo Alto Networks. And this is my co-speaker, Zhaoyan, who is also a senior security researcher at Palo Alto Networks. We regularly share our thoughts on different industrial conferences, try to share our idea with the security communities. So our research field cover from the mobile security to web security, network security. Currently, is the IoT security. We also a big fan to use the data analysis technique, like the deep learning techniques, to improve the detection technology as well. And we also, in our spare time, we also spend some time to do the fuzzing things and to report some vulnerabilities. And so in this presentation, I will start with the IoT and the honeypot and explain why it is challenging to build a honeypot for IoT devices. And then to conquer these challenges, we propose the idea to use the intelligent interaction. It's an automatic way and an intelligent way to build a honeypot for IoT devices. And in our system, there are two critical components, IoT scanner and IoT learner, which will try to automatically collect the behaviors from the internet and then use the machine learning techniques to train our honeypot to use the best way to interact with the attackers. So the honeypot, which is the very old topic, and it is one of the common methods to discover zero-day vulnerabilities that is widely used by security researchers. It's a system that is set up to act as a decoy to lure the cyber attackers and to detect and study attempts to gain unauthorized access to the system. So all of the traffic to the honeypot can be considered as hostile. And the first began with the 1997. People come up with the idea of honeypot, and since then, thousands of honeypot projects have been proposed. And if you search in GitHub, you at least find a thousand of them. So in the honeypot research area, there are two categories of honeypot: high interaction and low interaction. So their names are self-explanatory. Low interaction honeypots are nothing more than an emulated service that is frequently targeted by attackers and give attacker a very limited level of interaction, such as the popular one called popular HoneyD. On the other hand, high interaction honeypots are usually full-fledged system, use a real system for attacker to interact with, and they can just try to study how the attacker behaved after they gained access to the system. And another topic, the IoT, which is a very hot topic recently. I don't need to mention too much here because according to the Gartner survey, an estimated 20 billion to 50 billion IoT devices are IoT devices are IoT, which is a very hot topic, recently. So, and also, on the other hand, we are running out of time with the IoT security. I think you may have already heard about plenty of news regarding the massive attacks on IoT devices. This is because the IoT device is exponentially increasing the number of potential targets for cyber criminals. like the well-known IoT device exploration website Zhaoyan had reported, millions of IoT devices are exposed in internet without proper protection. And therefore, finding vulnerabilities on IoT devices become the front line of the battle between white and black. There are many ways to solve the IoT security problems, but all of them starts with the very first and the critical step: gather attack samples and analyze them. Then we can design different detection mechanism or prevention system. So Honeypot is the best way to discover zero-day vulnerabilities with a low cost, and that's the reason why it is important to build a honeypot for the IoT device. So the first question you may ask could be why the building IoT honeypot is challenging, because honeypot is a very old topic. Why would we just speak this topic again? To answer this question, we have to understand how attack on IoT devices works. Taking the remote command execution attack as an example, and also this is the most prevalent attack for IoT device. Basically, attackers craft a request and embed some malicious command in it. Due to the vulnerable implementation of the IoT device, the injected command will be executed on the device, and the device will get compromised. So, and the standard the standard template of the injected command is composed by usually a wget command to drop the shell file to the local device from the attacker's remote service, a chmod command to assign permission privilege to it, and then a command to execute the shell file. So, but the real attack is not this simple based on the traffic we have captured. So because capture this kind of traffic is quite easy for any honeypot. But the problem is that attacker will check whether our honeypot is a real IoT device, or whether it is the specific vulnerable version that they are targeting to. So after they confirm that our honeypot is a right IoT device, then they will launch attack and send the exploration packet. For example, here is a very simple example. To attack the Cisco Firepower management server with a version 6.0.1, attacker will send an HTTP request to the URL with this specific version number in it. They believe that only the device in that specific version can handle this request properly. If our honeypot return 200 OK response, attacker will continue attack and send the malicious packet just with the injected command like I just introduced before. However, if we reply other kind of response, like the 404 not found response, attacker won't send any request at all. And of course, this is just a simple example. From the traffic we have captured by our honeypot, we have identified more than 15 different ways that are utilized by attackers to perform the pre-attack check before launching the real attack. I will pick several of them and explain them to you so that you can have a quick idea on how challenging to build a honeypot for IoT devices to really capture the malicious traffic. So HTTP protocol is the most common one used by the IoT devices, and also this is a quite simple one for remote configuration and management. Nearly half the TCP traffic we have captured using this type of this protocol, and it is commonly used by attackers to perform the pre-attack checks, and also their actual attack. Based on the status code, we explain them one by one. Like the response code with the status code 200 OK usually contains more information about the device. For example, the most frequently used URL to check whether the device is a IP camera is get status.cgi, and the correct response should contain the configuration of the IP camera also in the correct format. Similarly, URL to check the routers is the current setting.html, and the correct response to it should contain the routers information. Attacker will pass the response before they actually launch the attack. So response with other status code may also indirectly leak IoT device information, and they also be used by attacker to check to perform the pre-attack check, like the www authenticate field in the response header with the static code 401 unauthorized. We have identified a lot of attacks after we reply the response with the value of this field, like Netgear R7000. Another example is the response with the status code 404 not found, that usually indicate the file is not found. It really contains nothing special besides the standard template, right? But some of the IoT devices, like the Ziva XEL modem, they do customize the 404 not found response page by add some additional information to it. And if we want to behave like this type of modem, we should be able to simulate the same page by also add some additional information to it. Besides the HTTP protocol, other IoT-related protocols or even the customized protocols can be also used to perform the pre-attack checks as well. For example, we identify that attacker used the MCTP protocol to get the attribute of the device before attacking it, like the KGuard DVR. The similar check has been found in the HNAP protocol as well. For the customized protocol, like the UDP port 43413, attackers may send 8 bytes of 0 to the honeypot in order to determine whether the host is a net core router which supports this customized protocol. Then they send the exploration package. So in the previous example, they are quite simple because we just need to return a fixed response every single time. But we do detect some attackers. They examine the response content that will change each single time. For example, some attackers use the command execution result to check whether the whether our honeypot is a vulnerable IoT device or not. So for some remote command execution attack, the output of the command can be viewed in the response. Therefore, some attackers will first embed an echo command to print some random string, and then check whether the response page contains such a random string or not, so that they can make sure whether their code can be executed or not. So obviously, the random string changed every single time because they want to check whether the device has been patched or not. So only after they confirm that our honeypot has not been patched, so they will send the request they will send the real malicious traffic. So in this example, although we can detect the remote command execution traffic, but what we actually want is a real malicious command, not the echo one, if we cannot behave like the real device. And since the real injected command contains the URL to the malicious shell file, and it's very useful since we can download this shell file from the remote server and analyze them. So based on those examples, I hope you can get the message that it is hard to capture the malicious traffic on the IoT device without simulating the correct IoT behaviors. If our honeypot cannot reply the correct behavior that is expected by the attacker, the chance to capture the real traffic will be very low, and also the chance to discover zero-day vulnerabilities for IoT devices could be quite low as well. So to conquer those challenges, our first step is to adopt traditional ways to build a honeypot. So ideally, high interaction honeypot should be able to pass those pre-attack checks, and we can just we can behave like the real IoT device. So the most straightforward way to build IoT honeypot could be just to purchase all kinds of IoT devices, from the IP camera to the auto vehicles, and use the physical device to build a honeypot. It works in theory, but in practical, at least for us, our budget cannot afford purchase all of them. So this way that doesn't work for us. An alternative way could be use the virtual IoT device for honeypot, like download the firmware image from the official website and run it on some device. But the fact is that the majority of the IoT device does not provide any firmware image for downloading. And even though for the available firmware image, the most advanced technique can only launch 40% of them in the non-IoT hardware. So which means that this way doesn't work for us either. That is the reason why all of the existing projects for IoT honeypot choose to use the low interaction style, such as the IoT Pot, Zhaoyan, and others. Based on our investigation on them, they just manually implement some logics and to simulate certain behaviors of certain IoT devices. And it's very time consuming to support all of the IoT devices, and it's hard to know how they behaved due to the lack of public documents. And also, of course, those kind of low interaction honeypots cannot pass the checks by the attackers. So the effectiveness of those honeypots will get compromised a lot. So now we are facing the dilemma, which is none of the traditional ways to build a honeypot can be used in IoT case. We have to come up with some new way to build a honeypot for IoT device. Therefore, we propose an automatic and intelligent way to build honeypot for IoT devices with zero knowledge about the IoT behaviors. We call this intelligent interaction. So there are two keywords in our approach: automatic and intelligent. For the keyword automatic, we design a module to actively probe the IoT devices on the internet with the request that we have captured from the attackers. And then we collect the responses from them. And all of the responses can be considered as the behavioral knowledge that we can use to interact with the attackers to make them believe that our honeypot is a real IoT device. But it raises another problem when we implement it, is because for specific request, we could get hundreds or even thousands of different responses from different IoT devices. But attacker may only expect only a few of them. And so if we just randomly return randomly pick a response from the scanning result, it would be very inefficient. So that's the reason why we propose a second keyword, intelligent, and we leverage the deep reinforcement learning to train our honeypot, and it helps us to learn the best way to choose the response from the interaction experience with the attackers. So in the rest of the presentation, I will just spend more time to discuss the detail to implement those two modules. So this figure shows how the overall of our system. So Imagine that attacker send a request to our honeypot, and we have never seen this request before. Things assume that we start with zero knowledge about the IoT device. So the first step is to save this request in a table called a raw request in our database, and return a fake response just for the first time. Then we have a module called the IoT scanner, which will periodically fetch the captured requests from this table and send them to the IoT devices on the internet. And of course, we maintain a large number of IoT devices that is public accessible from on the internet. And then the scanning result will be stored in another table called a raw response. And as I just mentioned, that will be the raw knowledge about we collected that can be used for the future interaction. And so if the same request was sent to our honeypot again, at the very earlier step, we can just randomly pick one of the response we have scanned and return it to the attacker. But we also keep record of all of the sessions. Like one we return certain response to the attacker, and the session table tells us what's the next step of attackers, whether he or she send another request or just be silenced forever. And it can tell us whether our response, our choose decision is correct or not. So with this session table, we have the IoT Learner module, which will try to pass this session table and use the deep reinforcement learning module to eliminate the unnecessary response. And then actually we just assign a probability to each single response. And this assignment can guarantee us to have a best chance to capture the real malicious traffic. And basically, that is the overall of how our system works. And then I will explain the first module, the IoT scanner, and Zhaoyan will explain the second module, IoT Learner. So the first step to build an intelligent interaction honeypot is to use this scanner to scan the IoT devices on the internet. And so we just try to do this in the polite way, and so we customize our scanner, because our scanner is pretty standard, and we do apply several heuristics to filter the things we need to scan, and to make the scanning result more close to the IoT, and also make the scanning process more efficient. So the first one is we just maintain the IP list, which is have an IoT device at the back. And comparing to the 4 billion IoT address space, the number of IoT device is a very tiny portion. So because we only want to scan the IoT device, and because it's IoT scanner, then we maintain the IP list for the active IoT device. And our source come from the both the online platforms like the Senses, Zoomeye, Shodan, and we also have our own scanning tool like the mass scan. So basically, we use scanning tools to collect the basic information from every IP address, which is exactly the same as this online platform did. So and we just want to keep our result more fresh. Then we identify the IoT devices by searching the predefined patterns like keyword, and to to pinpoint each IoT device. Then, so we collect around 40,000 IP address, and with various of type of IoT device from different brands, and also different versions as well. And then that is the IP pool that we will use to scan with. Another customization is the port number. And since we do not want to scan all of the ports, because our IoT device may only expose several of them for the interaction. For example, the Xing, around 70% of the routers open the port 1900 for the UPnP protocol, like to facilitate the device and the program to discover the routers and their configuration. And nearly every IoT device that provide the remote management through the embedded web server, they usually expose the port like 80, 8080, and 881. We also monitor and scan the ports used by the protocols that is heavily used by the IoT device, including the XMLPP, COAP, and MQTT as well. So here's the list of ports that we have identified from our analyze and also the public surveys. And we prioritize to scan the traffic on those ports first. And one of the critical input to our scanner is the request we captured from our Honeypot. In our database, since last December, we have stored around 18 million raw requests in total. And we observe that majority of them are clearly not IoT related. Therefore, we perform a filtering process to eliminate those kind of requests. As this figure shows, for example, nearly half the capture request does not contain any payload, and other traffic like the BT using the BT protocol, the MS-RDP protocol, they are clearly not the IoT related. Also, for the UDP traffic, they are also the majority of them is some contain some just a random thing that we also clean those things up. So by applying those heuristics, we successfully reduced the total number of raw requests that we used to scan from 80 million to less than 1 million, and then we combine the similar or same request together, and then the things we left, the number of requests we left is around 0.4 million. And this is just a number of distribution of the traffic we captured for each port, and we have more detail about this in our white paper. Due to the time limitation, and just skip this part. So at the last, the very important issue is that when we use the captured traffic as a content to scan the internet, it is important to filter out the dangerous ones to avoid attacking other machines. In our system, we leverage multiple heuristic methods and also existing detection tool like our firewall, the snort rules to detect them. Once we detect that there's malicious things in the request, we will mark it and won't use this to scan, because we have at this step we should have already captured the things that we want. So for example, the remote code execution is the most used one, and the attacker can put the injector command in every kind of a different part of the request, like in the SOAP body, in the UPnP packet body, and sometimes they also encode their injector command in some ways, and we also apply different ways to detect them and filter those things out. So then we just deploy our IoT scanner on 2 machines in our lab, and we put and then we just put all of the filter requests from the raw request table to a Redis queue, and we scan. Our scanner will periodically fetch the request from them, and then we send 300 different requests at each second, and set the timeout at 3 seconds. To speed up the scanning process, we also tend to reuse the established session, and then to send the request. So this is a roughly result that we get for the scanning result. We finished the scanning process after 2 weeks, and for all of the 4.4 million of raw requests we have captured, and those will be the knowledge that we will leverage on to reply attackers. And as I mentioned, you can see that the number of response we have collected is so many, and it's very inefficient to just randomly pick one to interact with attackers. And that's the reason why we have a second module to leverage the machine learning techniques to make it work. And Zhaoyan will try to explain this module in more detail.
I will introduce the second component called the Iot Learner. The Iot Learner is trying to make the IoT honeypots to be smarter to handle different kind of scenarios we encounter. So as we just talked, we have actually encountered a lot of challenge. Is we collect a lot of the responses from the IoT scanners. So the question is how we can actually identify the appropriate response that actually we can use and to respond to the possible attackers. So as I showed in the slide, so the solution we're trying to use is using some learning techniques, which is called reinforcement learning. So as all the people know, it's a kind of AI techniques has been commonly used in recent days for different kind of problems. So we're trying to use it for our purpose. So the flow actually, the learning starts from we receive a request, and we need to identify each state after we receive this request. So we have a first component called state locator. State locator will try to search from the request received and find what's the current status for each request. And then we will go past to a selector model. The selector model will actually use the information we collected, including some response session tables, all this kind of information we collect, and select appropriate response to them, to select the appropriate response and reply to the possible attacker. And all this kind of interaction will also be stored back to our database and for the second round of the learning. So let's start from actually examples we receive in actually a real world interaction. So the request we receive is under the root path called HN API. So this one will, sorry. So when we receive this request, we actually can search in our database to see what will be the possible response we can get from the previous IoT scanners. So as listed, there are four different kind of possible response from different kind of hardware, IoT hardwares, and then we fetch this kind of possible response and use our selector to do the things. At the first step, we don't have no knowledge about that, how we can possible response. So the easy solution is we start from a random selector, which basically means we randomly select one of the response and send it back to the attacker. And then we keep monitoring what will be the following interactions with the possible attackers. And also at the same time, when we actually start the interaction, we also store all the information we collected, including the IP address, the port address, all the things back to our database and for collecting different kind of knowledge. So before we continue, we need to formalize the learning problems that we actually encounter in our scenario. So the problem encounters, we have several like terminologies. I don't want to introduce too many details. So, but we just mentioned like when states, actions, and transaction probabilities in the typical learning program, we can map it in our problem domains, which becomes of the current incoming request, and also potential response set, and also the probability of the next request. So to further understanding what we mean of that is we list the example here. So the example is, as we showed in the previous slides, is when we receive that, so we will have a different kind of choice what the response we will have. So we were trying our best to select each of them and to collect knowledge we have. So after we collect this kind of knowledge, we will summarize it as a Markov decision process. And each state, each orange circles actually implies a different kind of response. And the black box shows the state that will reach after we respond each different kind of things. And the probability shows that it's actually very interesting. We monitor the different kind of interaction. We see it's like if we receive a response with different kind of response, there are some probabilities for the transaction. For example, from the response 3, you can see that there's like 0.2 possibility you will reach the termination, which means the possible attacker won't send any further interaction with us. But there's like a 0.8 probability of that the interaction will still continues. The attacker send another request which trying to find the ping.cgi in our problem domains. So this is the model we're trying to learn from, and the method we're actually using is the Q-learning. The Q-learning is like a standard technique that I think most of the people know how actually the Q-learning works. I don't want to introduce too many details for that, but I want to introduce you how we actually set the reward for each steps. So this is one actually real-world cases that we find for a possible attack to our honey nets. And you can see we label different kind of transitions between different requests and states. And we mark them with different kind of labels to say what will be the probability, what will be the possible outcome of that. For example, we find some like get status CGI, which has a network IP camera past the disclosure vulnerabilities. And also another one called get prior.cgi, which actually have a privilege operations vulnerabilities. For different kind of vulnerabilities, we manually assign different kind of rewards to them, which will help us to understand them better and also to apply them to have the better rewards to actually let us to expose different kind of attacks. So these slides will list some like some result of our improvements. So based on our current data set, as Tongbo has introduced, the total amount of data is still very small. But from this kind of small data set, we can have some improvement compared with a random selection response for that. So as this figure can show you that it's actually, we can achieve better performance compared with the random selection. So even though you probably don't see a very big difference between them, but the learner is actually a very long-term thing. So the learner will run a lot of time and continually to accumulate different kind of knowledge. And so that's why we believe that this learner mechanism can actually help us, help the honeypot itself to improve itself. So, and all the processes automatically. So we think it's could be a very helpful to further improve our techniques. So the real world is also not perfect, the same as our honeypot. So if we use the IoT learners, we encounter some real world problems. So the problems we have is that we find that there are too many possible responses and the costs the states of each the states of our learner is too big. So that will cause the learning to hard to converge. So the next step we were trying to do is actually we want to cluster different kind of response into like a limited number of different cluster to represent some response. So the method we actually use is also another technique called latent Dirichlet allocation. This is a kind of a technique we use to actually merge similar responses. So why we actually use the LDA? So LDA, first the reason we use LDA is actually LDA can work on some raw corpus and for the feature engineering, because the only things we actually can collect is the raw response. So the LDA can purely just work on the raw response, the texture features of these raw responses. And also the LDA can efficiently actually cluster the texture data. And more importantly, the LDA kind of to summarize different topics of each request. And the topics, which actually means is unobserved groups that explain why some part of the data are similar. So the heuristic behind that, why we use LDA, is IoT devices, they commonly use a lot of libraries to host their service. It's very possible they use very similar HTTP servers to host their service. So LDA can actually help us to understand that maybe this device uses this kind of service. So the LDA solution, we start from some terms. It's documents, terms, and topics. So in our problem, the documents is actually the response itself, and the terms is we split each response, the raw text, by some predefined delimiter, and the topics will be the outcome of each of them. So the example we have in the following slides is we actually analyze the HTTP traffic we receive from possible attackers, and we find this kind of response from the routers. So we found these routers actually they have 6 different kind of vendors, and we summarize 15 different kind of topics for them. So this is one visualization of our LDA result. So how we can actually verify that our result actually prove that they show some topic of that? There's a box at the end. You can see that this is a kind of a common common open source web servers. Actually, they can cluster things together. So you can see they all have this kind of strings in their row response, so which possibly means they are just have this topic of the same libraries. So as a conclusion, from the talk from the research we have done, so we actually introduce some challenges we have to build the IoT honeypot, use the traditional ways, and also we utilizing. Also we summarize some we utilizing automated and intelligent ways to build the honeypots. Lastly is we discover some interesting attack checks and some explosion on the IoT devices. So that's actually the answer of our talk. And welcome for any questions. Yeah.
Hi. So when during the initial phase, when you forward the request to the real IoT device and get the response, if it's a real attack, aren't you risking attacking a
Yes.
real public device?
So this is actually a very good question. I think maybe a lot of people read our research work will also have these questions. So we have actually these slides. Probably not showing here. We can let you watch the slides one more time. So basically, what we do is we need to carefully to filter possible explorers we have. We collect it, and we won't send this kind of request to the device on the internet. So how we do that? We actually do a lot of filtering. So some possible ways is we filter through some IPS signatures, IPS system, to actually filter a lot of them. And also we also use some reputation based, for example, if we think this this possible attacker is from some maybe low response some IP that we have no knowledge about them, we possibly won't send them because it's very risky. It's very possible risky. And also we use some manual work to manually check some of them, so if necessary. Yeah.
Thank you.
Thanks.
So very impressive work. I just want to check, ask a question about the time you build a database to try to query a real IoT device. How do you know those devices are actually not another honeypot or someone mimic?
Yeah, that's actually, be honest, we don't know whether it's another honeypot or not. It's possible there's another honeypot or not. And actually, from our traffic, we actually find some of the traffic is from another possible honeynet. So yeah, we don't discriminate very much about them, but we still have some either signature-based ways to verify this is, or maybe reputation-based ways or knowledge-based ways to filter these kind of things, to make our database as accurate as possible. Cool, thanks. I think that's it, right? All right. So thank you everyone to join the last talk and enjoy your parties.